It is part 2 of section 16.6. In the first part, we studied parametric representations of surfaces. Here, we'll try to find a formula for the area of parameterized surfaces. Any bounded surface can be approximated by a collection of planar patches, which are parts of tangent planes. So the surface area can be approximated by the sum of areas of such planar patches. The sum is a Riemann sum, and the surface area is the limit of Riemann sums. So we are using the same idea explored earlier for various integrals. Let's see the recall. The plane passing a point x0 having a normal vector v, which has 30 components, a, b, c, can be formulated as this dot product equals 0. In detail, we can write this equation. You learned this one earlier. Now, we'll find the tangent plane to a parametric surface given by this transformation. Then here, if you consider R sub u and R sub v, then they are your tangent vector, so that the normal vector can be obtained through the cross product of these two vectors. So what we need is a normal vector determined by R sub u cross R sub v. So we'll use this one as a normal vector, and we have a point, and then we can decide the tangent plane. We have a definition. A surface S is represented by R is smooth. So now we define smoothness of a surface if the cross product exists and non-zero over the whole domain, then we say the surface is smooth. And also the tangent plane is the plane containing these two, R sub u and R sub v, and eventually, if it is non-zero, then normal vector must be R sub u cross R sub v. So we define tangent plane in this way. So practically, we'll try to get tangent planes using that cross product. Okay. Let's see the example. Find the tangent plane to this surface. Okay. Now, here, if we write down the transformation as a function of Ru and V, then it is a 30 component x is u squared, and y is a v squared, and z is u plus 2v. Okay, so let's try to get normal vector. Okay, so that R sub u equal u derivative. Now there is 2u, that will be 0, and that is 1. R sub v, v derivative, that is 0, and that is 2v, and that must be 2. So the cross product, R sub u, R sub v, okay, that one is determinant of metric ijk, and this vector, that vector. So imagine this one. Here we have ijk and metric having the 3 vectors, and try to find the determinant for I Now eliminating this row and column, and AD minus BC minus 2V for J, eliminating this row and column, and now that minus this one, minus 4U, right? Minus 4U. And then here for the last one, eliminating that one, we have a minor here, that product minus that one. So that there's a here 4UV, right? Okay. So we have, for every point, we have the normal vector. Now we have to evaluate this normal vector. Then we can find the tangent plane. So we have to find U and V. Okay. Now this information, data, is for X, Y, Z. That means X is 1, Y is 1, Z is 3. So that here, from this one, from this data, we can see X U squared equals 1, Y V squared equal 1, and then Z, that is U plus 2V equal 3. From this one, U and V must be plus minus 1. Now, to satisfy this equation, we have to have U and V equal 1, like that, right? So the corresponding point in UV domain is 1 and 1. Okay. Along with this information, it can be now minus 2, minus 4, and 4. And we use that information here. Okay, so we have a point and normal vector, so that the tangent plane is formulated, and minus 2, that's A, and x minus x0, x0 is 1, and B is minus 4, and y minus y0, that is 1, and plus 4, which is C, and Z minus Z0. Okay, that is zero. So you can simplify if you want, or you finalize in this way, so no problem. Okay, now surface area is given in this way. Just along the surface element, just integrate this 1, and along the surface, if we get integration, then that is the area of surface S. Now, we consider the transformation from D in two-dimensional plane to S the surface, and that is R. And for example, this region is transformed by R to get that surface. Now, if we make a partition in UV domain, then corresponding partition in S can be made in this way. Now, we look at one patch here. Then the patch is given along with this sky blue color. And now, the area of this original patch is not easy to get. So we can approximate the patch by transformation of the tangent plane transformed along with the map. If this is delta U, there's delta V, then this vector must be delta U R sub U, and that vector must be delta V R sub V. Okay, so that the area of this parallelogram can be found quite easily through the measuring magnitude of the cross product made by these two vectors. We already know that. So for the small patch, it can be approximated by in area. Is approximated by the area of parallelogram. So that is exactly this one. Now delta U, delta V are constant. It can go out, and that is the magnitude of the cross product. So it can be used as a scaling factor for this transformation. Okay. So we can define the surface area. Now, a smooth surface is represented by this map, and here, now then the surface area of the S can be defined in this way. Area of S is the surface integral over S with a surface element. Now that is, along with this surface, this scaling factor, and integral over D. And that parameterization is from the domain D. So that means that ds is the same as now magnitude of this cross product, right? So that is for calculation. By using this formula, we can evaluate the surface area. Of course, this is the limit of Riemann sums. Okay. Find the area of the surface given by parametric equations. Okay. Now, for this one, and we'll use the formula so that we have to get first R sub u cross R sub v. Let's try to get it. R sub u derivative, that is now 2u, and v, okay, that is u derivative, there must be a v, and u derivative will make 0. Now how about R sub v? V derivative then is 0, and second one must be u, and that is a v. Again, R sub u cross R sub v. In your mind, you are thinking, I, j, k, and extra row, and here the matrix, okay? And that is for the first one, I, we have eliminating this one, that one, the minus this one. So AD minus BC, which must be V squared, for this second vector J. Now minus is 1, 2, 3, 4, that one. And here this product minus that one, so minus 2UV. And finally, the minus that one, this product minus that one, that is 2U squared. Right. Okay. Now, for that one, the length is R sub u cross R sub v. Length is square, 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 summation, square root of now v to the 4 plus 4u squared v squared, and plus 4u to the 4. Okay. The inside, that is a perfect square. That is in fact v squared plus 2u squared and squared, right? Okay, so that's the same as v squared plus 2u squared. Okay, we got that. And with this one, if we are using the formula, then area of surface is the same as integral now over d, and that scaling factor, that is u squared, that is v squared, right? Okay, that is v squared, and plus 2u squared and du dv. Now let's look at u and v. They are in a unit square in UV domain. Okay, so we may have this one, integral from 0 to 1 and integral from 0 to 1. Okay, let's say that is v squared plus 2u squared and du dv. Right? Okay, let's consider the quantity separately. Then for v squared, now v integration, there's no u, so the v integration will make 1/3 v cubed, so that 1/3 v cubed will make 1/3. And evaluating from 0 to 1. Now for that one, now twice of, okay, there's no v integration, so that along with v direction, the v integration is 1, and u direction, we have 1/3 of u cubed. Again, u is from 0 to 1, so that 1/3 will come out from that one. So it's twice of 1/3. So eventually, the final answer must be 1. Right? Okay. Okay. Now let's look at the change of variables, and the formula we obtained here. And when we consider change of variable for a two-dimensional representation, and for that one, we found that the dA in R domain is the absolute value of the Jacobian times the delta U, delta V. We did this one in chapter 15. So the Jacobian is determinant of that, so that we have that. And absolute value of this one is the scaling factor. Now we try to embed this transformation along with by using R rotation. So rather than two-dimension to two-dimension, we consider a two-dimensional function embedded in 3D. So the last component is 0, so that this original transformation can be embedded in 3D. So we consider that is a surface in 3D. Okay. Then, now by using the formula we explored earlier here, that one, okay, R sub u cross R sub v. We try to get R sub u and R sub v for this embedded representation. Then we have this metric and determinant, and we reach at that one. The magnitude of that cross product is exactly now same as that absolute value of this quantity, which is the same as that the absolute value of the Jacobian. So we may consider the map to get the surface as the change of variables. Okay. So we can say that this change of variable is a special case of general 3D transformation. Of course, this is also a change of variable. Here we summarize our arguments. R is from 2D to 3D. A representation of a surface S, then the map R can be viewed as a change of variables. The quantity, the magnitude of the cross product is simply the scaling factor for R. Okay. Okay, now we'll consider a special case. A surface can be made by the graph of a function z equal g of xy. So naturally, we can get the collection of points that is the graph. And also, the surface can be represented by this map. And collection of points is the graph of the function, right? So this is a special case, case of representation for surface. Of course, the function must be given, the surface must be given by this form as a graph of the function. Then we have this natural representation. Now, for this representation, we try to get the scaling factor, so r sub x, then from here x derivative 1, 0, g sub x. From here r sub y, 0, 1, g sub y. Then the cross product is determinant of this metric, and we reach at this one. This is the output of the cross product, and then the magnitude can be formulated in this way. So square root of g sub x squared plus g sub y squared plus 1. Okay, this can be easily memorized from here. Okay, from the equation, you can get z equal now g of xy. We may consider this portion as a function of x and y and z, and that is 0. After moving there to the left hand side is 0. So this portion is representing a level surface. And if we try to get the gradient of the level surface, then that is x derivative minus g sub x, and y derivative minus g sub y, and z derivative, that is 1. That is exactly this one. Now, in earlier, we, in chapter 14, we studied level surfaces, and gradient of level surface is the normal direction. In fact, that is fastest growing direction of the level surface. So that is exactly the normal direction. And cross product is always normal direction. And now, in fact, that is fastest growing direction. Okay? So you can easily memorize that one. Okay? Okay, find the area of the part of a paraboloid z equal x squared plus y squared that lies under the plane z is 9. Let's visualize the surface. That is x direction, y direction, that is z direction, and the paraboloid will be given this form, only the sides, and under the plane is equal 9, so that must be 9. So we try to find this side. Now that is naturally formulated in this way. From, if we go down, then bottom is a circle. That's 9, which means that now that is z equals x plus y squared, and z equal 9. If we translate the equal, then that is exactly that bottom. So it is a disk of radius 3, right? Okay, that is now D. Okay, so from D to the surface by using now r xy equal, here parameterization is x and y and x squared plus y squared, right? Okay, so from here we know that r sub x cross r sub y equal minus g sub x minus 2x minus g sub y minus 2y and 1, right? We know that. So here now the magnitude of that cross product is square root of 4x squared plus 4y squared and 1. So the area of surface must be double integral over d and scaling factor for x squared plus 4y squared plus 1 and dA. Now we know that the domain D is a polar region, so that we can use the polar coordinates. Angle is from 0 to 2 pi, and r is from 0 to 3, and the integrand can be written, these two portions, same as 4r squared and plus 1. We need now scaling factor for the transformation r and dr d theta. Okay, this is a theta independent, so theta integration can be done, and the result is 2 pi. And now for that portion, we try to get antiderivative. That must be a constant times, there's a half power, so that must be 4r squared plus 1 3 over 2, and we have to evaluate from 0 to 3, right? Now let's try to find this coefficient. Okay, in order to do that, we differentiate this portion. We try to make r derivative, and that must be 3 over 2, and inside the radical, and so it's a half power, and inside the radical the derivative must be 8r. Okay, let's simplify it. Then that one must be 12 along with that, and this half power and r. Compare this portion and that portion, they are the same, so we have extra 12. To eliminate this one, we need here 1 over 12, right? Okay, this whole thing, whole expression is an antiderivative of this one. Okay, so beginning portion, the coefficient is pi over 6. Now, when r is 3, that is 36 plus 1, so that 37. Power is 3 over 2, minus when r is 0, that's 1, so that 1. So we have this solution. That's the final answer. Okay. Okay. Now you can identify the surface quite easily for that one. X, Y, Z. Now if you consider x and z, then x squared plus z squared will be 4. So in xz plane, it's a circle of radius 2. So you can easily recognize. For this one, you may, okay, this is x, y, and z. You may get, okay, a, for some a, ax plus by equal, for some c, but or anyway, and CZ and plus D. You may express in this way. So try to find A, B, C, and D, and then eventually it'll be a plane. You can do it yourself. And for that one, yeah, you can get quite easily for that one. And hint is given. Okay. So, okay. Everything seems doable for you. Okay. That's the end of the section. Thank you.